Okay, so again, thank you for the nice introduction. Let me give you some introduction about the webinar we will have today. We are going to talk about the EMI design and troubleshooting with near-field scanners. It's something like a second part of my first webinar, but I will try to make a presentation that is full for people that not attended the first one. So today we will be working with near-field scanners, considering that you are interested in this problem. No, you have something that is called the victim, something that is receiving electromagnetic energy from some kind of culprit that can be intentional or unintentional. Intentional transmitters typically are systems that, for example, have some kind of radio frequency antenna or some kind of radio frequency activity that is desired. No? For example, you have a walkie-talkie or you have a telephone, you have one antenna and you are interested in radiating energy to the environment. This energy can arrive to a victim and can create the failures. At the same time, you can have unintentional transmitters. That means systems where you have hidden antennas and the electromagnetic energy that you are using inside of this product is being able to arrive at some distance to create problems in the same victim. To avoid these kind of situations, in regulations, we have the possibility to pass EMC test. EMC means electromagnetic compatibility and is the ability of a product to demonstrate that will not be creating a lot of problems in EMI or is able to support the EMI levels that are typical in some kind of environment, residential, industrial, or things like that. No? So when you go to the laboratory, to an external laboratory, you typically obtain results like this one. No? The idea is that you put the device on top of the table at some distance, for example, 3 meters, 10 meters, you put the antenna, and then from some specific frequency to another frequency, in this plot, I am working from 30 megahertz to 1 gigahertz, you have some kind of emissions that are over the limits. No? The limits here are in this red line that I am drawing in the screen. No? So on the right side, you see a typical situation where what we call a narrowband emission. Related with the resolution bandwidth of our spectrum analyzer, we are able to identify specific peaks at some specific frequency that, for example, can be harmonics of a digital clock. You have a clock at 50 megahertz, so you have harmonics at 50, 70, 90 megahertz, and you are able to identify these peaks because the resolution bandwidth of your analysis is smaller than the distance between these harmonics. On the opposite side, you can specify or you can be able to measure broadband emissions. That means that the emissions come in some kind of envelope or something like this, is something like a mountain, and you know that you have energy below this mountain, but you don't know where is the origin of this energy, at what frequency exactly is, and you know specifically this broadband emission is related with some frequency that is in your product. You need to reduce the resolution bandwidth to do this. So typically that people that is trying to solve this kind of problems is interested in reducing the emissions in some kind of level, like for example, could be something like this, no? So you are below the limits, I don't know, 6 dBs, 10 dBs, you can take some kind of margin, safety margin, to be sure that the full production is complying the rules, no? To identify the origin of the problems, we can use near-field probes. Near-field probes can be very useful for testing PC boards. So you are able to find aggressive areas, hot areas in your PCBs. We can test in cables. So we can identify we have some kind of common mode or differential mode currents in our cables. Or we can look for leakage in enclosures. This is what we will do today. But instead of using near-field probes, I will be using a near-field scanner from YIC Technologies. Remember, when trying to design an electronic circuit and considering EMI, we have some kind of culprit. We have some kind of victim. And you have some kind of coupling mechanism. Okay, this is the coupling mechanism. In coupling mechanism, we have two possibilities. This coupling mechanism can be conducted. For example, you have some kind of wires or some kind of metallic structure connecting the culprit with the victim, the chassis, for example, or can be non-conducted. That means the energy is going from the culprit to the victims through some kind of dielectric, the air or another dielectric in your system. How is the best solution to solve or to avoid any kind of problem? The first and best solution is to kill the culprit. This is very important. If you are able to locate in your system who is creating this energy, you will be able to apply probably solutions that are very cheap and very easy to introduce in your system. Additionally, you will not have the possibility to radiate with any cables or any enclosures in your product because the culprit is finished. The second possibility you have, sometimes this is not possible, is to increase the immunity of the victim. For example, you can work with a digital technology that is slower than the digital technology that you are using at this moment. And many people is able to identify where is the culprit. Many people is able to identify where is the victim, but it's not so easy to identify how is the coupling mechanism. When you identify the coupling mechanism and you identify that the coupling mechanism is conducted or not conducted, you have two different solutions to the problem. For conducted emissions, we are able to introduce filters. So we put some kind of inductors, capacitors, resistors, or ferrites in the middle of the path of the signal to avoid the path of this signal to the victim. When we have a solution that is non-conducted or a problem that is non-conducted, typically the solution is sealed in. But remember, these solutions are the third solution you need to try. The first solution to try is to kill the culprit. The second solution is to increase the immunity of the victim. And finally, if you cannot do that, you can introduce filters or you can introduce shielding. So what is important when you are working in your electronic circuit? Basically, three different elements. The first element that is important is the PCB. You have a PCB, and at the PCB level, you can create a lot of problems with the components you are using, with the technologies you are using, how the components are located on top of this PCB, and basically how do you do the stack up of the layout of the PCB. The second step in your product is cables. Cables are very important for EMI because cables usually are the most important antennas, the more efficient antennas in our systems. Remember that to be able to radiate or to pick up noise from the environment, we need something that is metallic and in a dimension that is comparable to the lambda wavelength of the signal. Remember this equation. If you have a signal at some frequency, that means you have a wavelength that is 300 over the frequency in megahertz. So you have the wavelength in meters. So if the dimensions are comparable to lambda, then be careful. This is the idea. Okay? When you are working in electronics and the size of your system is in the size of the signals you are carrying, then you can have the possibility to radiate or to pick up signals from the environment. So what happened at low frequencies? At low frequencies, the wavelength is bigger. Then you have more probability to radiate the signal if the system is long. Okay, this is what happened with cables. This is the first level, PCB. This is the second level, that is cables. And the third important element in your products is shielding. It's the possibility to put some kind of metallic enclosure around your product to be able to limit how much is the energy that is being radiated or received by your product. This metallic element is not the important thing. I mean the material. Usually any material, aluminum, steel, copper, can work very well sealing. There is only one exception. Is when you are working at very low frequencies magnetic field. For example, DC, 50 hertz, 60 hertz, 100 hertz, 120 hertz. These kind of frequencies, you are trying to seal magnetic field, are very difficult to control with a typical metallic material. You need special materials like mu metal. But if you are not in this low frequency magnetic field situation, any kind of material is able to solve problems. So where is typically the problem with shielding? The problem with shielding is in this area, is where and how you go in and out of your system with cables. Are you introducing some kind of filters in these cables? Or the leakage that you can create through slots and apertures in the shield. Okay, so this is what we will be reviewing today. We will have a system. I will do some demos to demonstrate this working. We will see how the leakage can be in my metallic enclosure. Then we will be analyzing what happened with cables, common modes and differential mode currents. And finally, we will review the PCBs that we have inside of this product. This is a hypothetical product. It's not a real product. It's with different PC boards and a small enclosure to demonstrate the technique, okay? I'm going to use the EM scanner. The EM scanner is a flat surface that has more than 1,000 small near-field probes. So you put the device on top of the scanner, and in real time, you have a picture about how is the activity in the product you put on top of the scanner. The other possibility for scanning circuits is to use the EM probe. Instead of 1,000 probes, we have only one probe, and this probe is in a one-arm robot, and the probe is moved around the circuit under test. So you can locate the origin of the signal in different positions of your PCB and working at different heights. Okay, but I will be using my demos the EM scanner to demonstrate the idea. What we have is something like this. It's a very big number of small cells that are below the device under test. And then we are able to measure how much is the magnetic field that is related with the currents in your circuit. If these currents are not controlled, then you have the possibility to create many, many problems. We can do basically two things. I will be doing in my demos one spectral scan and one spatial scan. What is spectral scan? It's the possibility to identify what frequencies are coming from the device under test. For example, you can identify the main frequency of your clock, or you can identify a specific harmonics. Okay, this is typical from digital circuits, or this is typical from circuits that are switching, like in power electronics. Additionally, we can find situations where we will identify some kind of additional emission like this one, okay? Something like this, for example. So what means this emission? This is a broadband emission. It's not related with the frequencies in my circuit. It's not related with any harmonic of my switching activity. This is the broadband emission, and is related with some kind of ringing or parasitic oscillation in your design, typically related with amplifiers, DC-DC converters, or some kind of layout error, okay? When you have a spectral scan, you can switch to the spatial scan. That means what? For any of these frequencies, or for all those frequencies, you will be able to identify where this energy is located. So you will find that in some specific area, we have a loop, or in some specific area, we have the origin of this non-controlled energy. And then you will be able to apply solutions in the firmware, filtering, shielding, doing what you think that is accepted by your product, and you can see in real time what happened. There is one possibility to scan spatially. That is what we call the interleaved scan. That means what? Doing a very simple movement in the prototype, measuring 2 times the emissions, we are able to have more resolution spatially. This is not very important. This is not mandatory, but in some situations can be very helpful to have more resolution to identify where the energy is. So if you work with these kind of tools, you will be able to see where your problems are. So you will be able to understand the root causes of your problems. You will be able to identify layout issues or cable issues or shielding issues. You will be able to do some kind of pre-compliance test before going to the laboratory, and you will be able to evaluate any kind of change you do in your prototypes before going to the semi-anechoic chamber. This is what you need, okay? What you need basically is the scanner. You can use the flat scanner, EM scanner, or you can use the, or you can use the EM probe. It's exactly the same. And the scanner is connected to 2 elements. One element is the computer, where we have a software that we call EM Viewer to be able to control the second important element, that is the spectrum analyzer. EM Viewer and the scanner are compatible with many spectrum analyzers we have in the market today from Rodan Suar, from Keysight, and other vendors. The bandwidth of this measurement can go from 150 kilohertz up to 8 gigahertz with a very high resolution and with very, very, very good sensitivity. So I think with this general view, you see what you need, and we can go to the demo. How will be done the demo? We have 1 hour of webinar, 1 hour, 10 minutes. It depends 2 of your questions. And I will be using several cameras to show you the experiments. Let's go to this camera here. Okay. Okay, what happened here? Why disappeared the camera? Sorry. Let's open again. Okay, here it is. Okay, this is the first camera. In the first camera, you can see a lateral view of my setup. You can see here the scanner. This is the product we will be analyzing. This is my arm. You can see a second camera, that is this one, where we will be able to see the surface of the scanner from in a top view to see the circuit. And this is the screen of my oscilloscope. We will be using one oscilloscope in some parts of the demos. And this is the screen I will be using to show you how is the software. Oh, sorry, what happened here? Something is working. It's happening. Okay. Okay. This way. This is the software, the EMViewer software that I will be using in the demos. Okay. So let's go to the first part of the demo. This is my product. I am using this. Let me see if you can see it this way. Okay. This way. Okay, my product is inside of a metallic enclosure, and I have only a power supply cable. The power supply cable is going through a very small hole here, and you can consider in a product you can have some kind of connector in any part of the box. Later I will open the box, and I have 2 different areas in the product. Okay. But the most important thing you can see is that I have here some kind of apertures. You can see here that is for ventilation. It's the same in the lower part of the PCB of the product, sorry. And I can power my circuit from these cables using this additional cable that is carrying something like 10 volts. Okay, so let's go to power the circuit. I hope you will be able to see inside. Let me see if I can go inside of the product. So you can see that when I am powering the circuit, let's power the circuit. Okay, I switch on the power supply with 9 volts. Okay, you can see that the red light inside of the product indicating that the product is on. Let's see what happens if you go with your product to the laboratory to pass radiated emissions. What you will have is some kind of antenna. I will be using this antenna here. Let's remove the camera here. Okay. So let's use this small dipole. In reality, you will be using some kind of logarithmic or biconical antenna at 3 meters or 10 meters. And I will be connecting the output of this antenna to my oscilloscope in channel number 1. Okay. Let me see if you can see what I am doing. Okay. This is the oscilloscope, and I'm connecting to channel number 1, the output of the antenna. So in the screen of the scope, you can see how is the output of the antenna in the time domain. Okay, let's see. Nothing interesting. It's very difficult to extract information from this time domain signal. So the first thing to do when debugging EMI is to go to the FFT. That means to see the frequency domain of this signal, something that is typically very useful. Consider, for example, like with a spectrum analyzer, I'm going to go from DC up to, I don't know, for example, 300 megahertz, 300 megahertz. And let me select 100 kilohertz for the resolution bandwidth. Yep. Okay, you can see here that I have some kind of emissions. This is the energy. Let me increase the size of the screen so you can see better. This is DC. At the end, we have 300 megahertz. And in this area, we have the mountains that are related with FM broadcasting. Let me switch off my product. When I switch off my product, all the energy that was in this area disappear and some part of the energy in this area. Let me switch on the soldering station in my lab. Okay, you can see that this is the activity created basically by my soldering station. Okay, so it's very important when you are doing this kind of measurements to disconnect as much as possible the products that are around your system, and additionally to know what frequencies you have in the environment. You will obtain probably the frequencies from 88 to 108 megahertz that are related with FM broadcasting. You have some kind of broadband low frequency noises created by switching mode power supplies, I don't know, your phone chargers or any kind of soldering station or switching device close to your circuit, lightning, using LEDs, I don't know, many things. Let me switch off my power supply, my soldering station. You can see that the energy disappeared. So this is the environment I have in my laboratory. If I am doing this measurement inside of some kind of shielding chamber, the ambient noise will be reduced, of course. So let's switch on again my product. Okay, so let's see. I have a strong emission in this area. This is something like 126 megahertz. This mountain is related with the activity of my circuit. So if you see my circuit, the energy is being radiated and received by the antenna. Sorry, the antenna is okay in this way. So the signal is being radiated by the circuit and is radiated by my system and is received by the antenna. But who is radiating this energy? We have two possibilities. Really, we have three possibilities. So let's go to my notebook here, and let me draw the problem. What I have is a circuit where I can identify exactly the metallic box. This is my antenna, okay, at some distance. And I have inside of my product some kind of PCB or PCBs. This is the enclosure, and this is the cables, the power supply cables. Okay, so let's consider if we can do some kind of general numbers. Let's increase the size of the screen for you. Okay, so how is the frequency where, for example, I am failing? I am failing in 125 megahertz. How much is lambda? Is 300 over the frequency in megahertz. This is what? Let me make a good calculation, 300 over 125 is 2.4 meters. So what is in the size of lambda? When I say that length must be comparable to lambda to have problems, that means that to avoid problems, you need to work with things that are smaller than lambda. How much is smaller than lambda? Typically, you can use lambda over 10 or lambda over 20. That means if you must be happy, if you want to be happy with EMI, then you need to put the length of your things smaller than lambda over 20. How much is lambda over 20 at this frequency? Lambda is 2.4 meters, is 2.4. 2.4 divided by 20 is 0.2. That it means is 12 centimeters. So what happened here? We have several possibilities for the emissions of this product. The first thing is that you can radiate with cables. So the energy that is being radiated by cables can be the one part of the origin of the emissions. So this is cables. The other possibility is the enclosure. But why the enclosure? Because in the enclosure, you have leakage, because you have apertures, or you have some kind of slots, you have some kind of display hole, or you have connectors, and you have big holes to put the connectors. This leakage can be a good antenna if the length of the slots are bigger enough. The worst length typically for cables and slots is to have exactly lambda over 2 or lambda over 4, because at multiples of lambda over 4, you have some kind of resonances. And when you have resonances in EMI, then you have the possibility to have maximum currents or maximum voltages. That means problems, no? So let's start to think or to analyze with the scanner how is the leakage from the enclosure. Then we will be working with the cables. And finally, we will be analyzing the PCBs, because if you are radiating with the cables or you are radiating with the enclosure, at the end, it's because you are creating the energy in the PCBs. So the solution must be tried at the PCB level. This is cheaper, this is easier, and this is more robust for the future. If you try to introduce shielding solutions, you will need to introduce some kind of gasket, or you will need to introduce some kind of more expensive solution in your mechanical design. If you want to filter in the cables, you will need to introduce capacitors, inductors, ferrites, common mode chokes, and this will they will need some kind of space, or they will cost a lot of money in production. But let's start with the leakage. So to analyze the leakage, what I am going to do is to put the closure on top of the scanner. Okay, let's see if you can identify exactly where I am going to put the enclosure. Remember that in the other side of this enclosure, I have exactly the same layout of the mechanical design. I have these 3, 6, 9, 12 is 12 slots here in the mechanical design. And these 12 slots in the lower part of the enclosure are on top of the scanner. If you want to scan this area, you can rotate the product, or if we want to scan this area, we can rotate 90 degrees the product, and we will be able to scan the 6 phases of your design. No? So let's go to the EM viewer. We open here, and the first thing to do is to create, let me close this one, a new project. Okay. Okay. We have now a new project. Now the system is trying to connect with, let me close this one. Sorry, let me open again because I disconnected the spectrum analyzer before. Okay, it's detecting, it's trying to detect the software now, the scanner and the spectrum analyzer. I am using a Rodan Swart FSH spectrum analyzer. I don't know what happened now. Okay, it's connected to the scanner and to the spectrum analyzer, and you can see that it's detecting the FSH. No, in my camera you can see the FSH is here. Let me show you with the camera. Okay, this is the FSH that is connected to the scanner. Okay, let's go continue here. Okay, now the first thing to do, for example, is to create a spectral scan. What means a spectral scan? I will be scanning the area of the product looking for some specific frequency range. No? So let's go here to specify some frequency range. For example, from 10 megahertz up to 250 megahertz. This is the frequency range I am going to scan with a resolution bandwidth of, I don't know, 120 kilohertz, perhaps 300 kilohertz. That means if you increase the resolution bandwidth, you will be less, you will have less resolution in frequency, but the analysis will be faster. We can measure peaks if we want. For example, we can measure, I don't know, 3 peaks, and we can specify what probes in my scanner are of interest for me. Okay, so let's put here the scanner exactly in row number 6 between columns P and AI. Okay, so this is what I am going to scan. I unselect the full number of probes. Let me from P to AI, this one, okay, this one, and then we go to row number 20. So it's number 20. I am selecting with green color the active probes that are exactly in the corners of my enclosure. I can identify some specific cells to scan what frequencies are coming from my product. Remember, the area with this kind of slots is here. That is because I am not selecting this area here. Obviously, you can select as many probes as you want, but remember that the scanning process will be slower. For the spectral scan, it's not necessary to specify all the cells below the product. We will do this when doing the spatial scan. You can specify some kind of amplification setting. If you have one external amplifier, this is very useful to increase the dynamic range of the measurement, or you can introduce some kind of attenuation setting if you are using an external attenuation. So I accept, and now I will be running the scan process. The software is setting the spectrum analyzer, and now is scanning. The scanning process is very fast, and when the scanning process is finished, okay, now the scanning process is finished, and the system is now detecting peaks. But now we can see the result of the scanning process. We can see here some frequency that is around 11 megahertz. This is 22 megahertz. This is 33 megahertz. This is 55. So it looks like these peaks are related with some digital activity. And we have here a broadband emission that is around 130, 125 megahertz. This is the mountain that was coming from our antenna. This is the energy that we detected in the radiated test. No, but remember, we are scanning below this product that is enclosed in a metallic area. So how is possible that the energy is going out of the product if all the product is shielded? Remember, the problem is not the material. I am using aluminum, steel, any material. The problem is not the thickness of the material, 1 millimeter, 2 millimeters, 3 millimeters, because we are in high frequencies. We are not in low frequencies. Independently that if you have electric or magnetic field, the problem will be related with leakage through the holes or apertures, or leakage through the cable. I am not scanning the cable, So the leakage is coming from the enclosure design. So to be able to identify where is the origin of some specific frequency, for example, I can be interested in identifying how is the leakage from this 11 megahertz. I can activate a spatial node. And with the spatial node, I can measure some specific frequency identified by the system, for example, 11.06 megahertz. Let's specify 300 kilohertz like the resolution bandwidth without changing. And now we need to activate the full number of probes below the device under test. So we do this, and we select all of these cells. It's not necessary to activate the other cells because my device is not on top of the scanner in this part of the system. So in this way, the scanning process is faster. So I accept, and then I can run the test again. So you will be able to see where the energy is located at that frequency below the device under test. Okay, so we can see that here we have a specific area. We have another point here, but there is this area like the most important area. To identify with more resolution, to identify with more resolution where the problem is happening, we can import some kind of picture. For example, let me open the overlay and let me import some kind of a picture. Let me go here. This is a picture of the enclosure, and you can adapt the size of the enclosure to the real size of the product. Apply, okay, and then we can see how the emissions are exactly in the area where we have the, let me open here, exactly. Okay, it's exactly in the area where we have the slots, okay? We can see the 3D view, and we can go up and down to see how the energy is coming from the product. Obviously, the leakage is in the lower part of the device, and the lower part of the device has a metallic wall that is exactly equal to this one, okay? So that is because with this picture, I am able to identify where is the leakage from my product. Okay? Remember what is happening in these kind of problems. This is the idea. Let's go to this picture. Okay, here. Let's draw one slide here. No, what happened inside of the product is something like this. Okay, let me see that this is the bottom of my enclosure, and I have several slots that are for, in this case, for vents. No, something inside of my product. Let me draw here another view of the product. Something inside of my product is creating emissions, and these emissions create in the lower part of the product inducted currents in the metal. So if you want to see how is the inducted currents in the metal, you will see that the inducted currents cannot follow the natural direction because they have this opposition. Okay. If you have an area where there is no slots or apertures, the currents that are inducted can circulate in a very good way. So the magnetic field that is created at this point by the original signal is cancelled by the magnetic field that is created by the inducted currents in the metal. If you are not able to permit the currents to circulate freely in the surface of your metallic box, then you will have this effect of distortion. And the effect of the distortion will create impedance. And if you have impedance, because you have current and you have impedance, then you will have voltage between different points of your metallic enclosure. And this voltage will excite the slots, and the slots are converted to antennas. The worst situation is when the longer dimension in the slot, in this situation, this one, The worst situation is when this length is equal to lambda over 2. This is the worst situation. So the solution typically is, instead of doing this kind of enclosures, slots that are something like slots, you can try this kind of design with small holes. And with the small holes, there is no so big distortion. And the idea is to make slots with a diameter or a dimension less than lambda over 20. If you do this, the behavior of the enclosure will be better. Okay, we can try to see how this enclosure is working in a full frequency range. For example, instead of doing this spatial scan, let's go to do a spectral spatial scan from 10 megahertz up to 250 megahertz again, with a resolution bandwidth of 300 kilohertz. And let's establish where are the probes. The probes that are of interest for me are from here. Let me see, to number 20 here. And I think it's this one. No, AE, and this one too. Okay, select. It's okay. Yes, it's okay. From my picture, I am looking at the picture. So I am activating exactly the probes that are below my system. So I accept, and then I run the test. This spectral spatial scan is different because now I am testing the full number of cells in the full frequency range. In my previous scan, I was scanning the surface of the product only for 11.06 megahertz. Now I am sweeping in the full frequency range. You can see that in this area, basically the most important frequencies are coming from this area here, that is 130 megahertz. And now the colors in the amplitudes goes to green. When we go close to the slots, you will see that the amplitudes start to increase. So typically, these green colors will be converted to blue colors, and this area here will start to have green, yellow, or red colors, depending of the frequencies of interest. No, you can see that again we can identify a frequency that is close to 11 megahertz, and we can see emissions at 130 megahertz that are distributed below the device under test. Okay, you can see that now the green color start to go to blue color because the amplitude that we have detected here is bigger. Okay, you can identify that as we go close to the slots, more activity is detected in this area. Now here is completely blue because the dominant energy is in the area of the enclosure of the leakage. You can evaluate with this technique different mechanical designs for your slots. For example, you are creating some kind of overlapping design, if you are evaluating some kind of gasket, if you are interested in this kind of accessories, okay? So you can see, or we can compare now, okay? We can see this in Zoom, and again, we can introduce the overlay if we want. No, it's not necessary, but sometimes to introduce the overlay, it's better to understand what's happening in your circuit this way, okay? You can see this. So when I am identifying, when I click here and I say, can you tell me where is this energy, this 132 megahertz? The system will give you here where is specifically located. But if you say, no, I am interested in this frequency, okay, let me go here to this peak. You will see that this in this frequency. Where is the third harmonic, the fifth harmonic? The fifth harmonic is coming from this area. Or where is the third harmonic? The third harmonic is coming from this area. So you can identify exactly in what part of your enclosure design is the leakage you are identifying. Let's open the product so you can see what is happening inside of a product. Let's remove the box and let's go inside of the product. Okay, I have basically this way. I have basically, let me see, I have basically two PCBs. One PCB is in the bottom of the enclosure, and the other PCB is in this area. This is the power supply, and this is my digital circuit. And you can see that I have two different cables. No, let's try to explain what is in this area. Let's disconnect my tablet so I can open a new page for you, and let's take a picture of the screen so I can this way. Okay, okay, and now we will use this picture so you can see my notes. Let's open this picture. Okay, this is a real picture of the product. So what I have here is a microcontroller board. It's a microcontroller board with some display at the bottom. This circuit is powered by 5 volts that are coming from a DC to DC converter. And this DC-DC converter is being powered by 9 volts, for example, 9, 10, 12 volts. No? So in my picture, this is the input of the 12 volts or the 9 volts, 9 to 12 volts, something like that. This is the cable. This coming in this direction, you can see, is doing something like this, and is going to the VIN of the DC-DC. So this is in yellow color. This is the output, 5 volts, that are coming in these wires in this direction. Okay? So what happened, basically, you can identify how the cables that are carrying the power supply signals are with a layout that is close to the slots for ventilation. This is a general rule of EMI when designing circuits. Never you need to put aggressive elements close to slots or apertures because you will have more probabilities to create coupling mechanism. No, I mean, if we draw this in a general view, okay, if this is my enclosure and you see here the slot, this is the slot, okay. If you have a PCB and you carry the wires close to this area, you have more probabilities to radiate, to excite the antenna, and to radiate that if the cables are far away from this enclosure, from this slot. No? The emissions will be reduced a lot. Let's see if we can test this with the scanner. Okay, so let's go here and let's repeat at, for example, 11 megahertz. No, 11 megahertz. No, let's try, for example, let's see, this frequency is this area. Okay, it's in this area here. You can identify clearly. Okay, if we change we remove the overlay, you can see that the 120 megahertz, it's 125, 130 megahertz is coming from this area, no? Let's try to repeat the test, the spatial scan. Let's repeat the spatial scan for 130 megahertz with a resolution bandwidth of 300 kilohertz. Okay, and then in this area. Now let's remove this area so we can from 14 from here. We reduce the area of scanning to accelerate the process. I am interested in the area of the slots, and then let me run the scan. Okay, so now I reduce this screen. Okay, and then you can see what happened. Let's start setting the spectrum analyzer. Okay, we can see here the emission that is coming from this slot, okay? And let's repeat the scan considering that we move the cables. Let's try if this is the origin of my problem. What I'm going to do is to separate the cables from the slots. Okay, let's put the product in the same position. Okay, right. And now look at this. My cables are far from this area here. Okay, so let's see what happened, and we will compare. Okay. Okay, and now let's go to the scale options, and let me remove the auto scale option, and let me put here from -3 minimum value to 17, from -3 to 17, and now here the same, from -3 to 17. So really we can compare. So look at this. This is the leakage from the same holes. Let's remove this. This is the leakage from the same holes with the cables close to the slots or with the cables at some centimeters from the slots. It's recommended that any cable with a high frequency activity must be far from the slots, I don't know, something like 1 centimeters, 1.5 centimeters, 2 centimeters, as much as possible. But if you obtain 1 or 1.5 centimeters in distance, that you will identify a very big reduction of the emissions. But look at this. If I run again the test at 11.06 megahertz, again, accept. Now I am going to scan at the first harmonic of my digital clock. You will see how is the activity. Okay, you see a strong activity. It's the same like before. Why? Because now the activity of the digital clock is in the same position. The activity of this first harmonic or the 33 or the 55 is in the PCB, and the PCB is on top of the slots. Is in the same position, so the coupling is being the same. The 125, 130 megahertz activity is going through the cables, and that is because separation of the cables reduce the coupling at that VHF frequency, but we don't obtain any change at 11 megahertz that is coming from the PCB. Well, remember, with this technique, you can evaluate different designs of your enclosures, the size of your slots and apertures. You can evaluate gaskets. You can evaluate absorbing materials that you can put in the internal sides of the enclosures. A lot of things can be done in this situation. Additionally, if you don't have the electronics, consider, for example, you don't have the electronics. We will have time, we will do this experiment. If you don't have the electronics, you can put inside of your enclosure some kind of comp generator. A comp generator is a circuit that is able to create a lot of frequencies from a low frequency to a final frequency. Then you put inside of the product this comp generator, and you can evaluate how is the behavior of your enclosure before the design of the PCB has been done. Because typically in a company, the PCB design and the mechanical design are running in parallel, no? So to evaluate the mechanical design is possible in some way with this technique and using the scanner. If we have time later, I will do this test for you. Okay, let's put again the cover on top of the scanner. And now consider that we are interested in testing the cables. Okay, so for testing the cables, I will be using this small blue tack element to fix in place, and this tape. Let's see if you can understand what I'm going to do. Okay. The second possibility to radiate from my product is not from the enclosure. The second possibility is through the cables. In my product, I have only one cable, is the power supply cable. But I can do that, okay? Something like this. Okay, you can see I am running the cable. Let's see if you see the top of the scanner. Okay, now I will be interested not in the enclosure. I am interested in this cable. When interested in radiation from cables, you need to remember that energy in cables can run in common mode or differential mode. Let's go to the notebook here. Let me introduce another sheet. And let's consider that we have a system and we have two wires, red wire and black wire. This is, in my example, this is something like 12 volts and this is ground, okay? So what we have here in these two wires is differential signals. That means I have this differential signal. For example, I don't know exactly how is the consumption of this circuit, but consider I am consuming, I don't know, 200 milliamps DC. Remember, this is DC. So if you plot this current in your scope, this current in your scope would be something like this. It's DC. Additionally, in this cable, we can have differential mode noise. That means what? You have noise that is going out from your product and is returning through the ground line. Okay? So really, the current in your circuit will be something like this. You have a DC level plus some kind of noise related with the activity in your circuit. This is the differential mode that can create problems in some kind of victim. Additionally, in blue color, I can plot what means common mode. Common mode is the current that is going in this direction, and is returning through some kind of unknown path, typically capacitive or direct connection to some kind of metallic chassis, or for example, some kind of the earth, the floor, or my body. Typically, this current is very difficult to control. Why we usually don't have problems with differential mode currents? With differential mode currents, usually we don't have problems because this cable is usually very close to the first one. That means what? You have a very, very small loop. Differential mode currents usually don't create radiated emission fields. Why? Because the forward path is very close to the return path. No loop. Then you will be exploiting the cancellation effect. Let me draw this for you. Let me remove this one. Let me draw the red cable. And let me draw the black cable, no? The ground cable. So what happened at this point, P? At this point P, the current, the differential mode current that is going in one direction, in the red color, is creating some magnetic field. But the return current is the same value, is creating the opposite field. I mean, the total field will be 0. If you move this cable far away from the first one, what happened is that the second field will be smaller, and then the magnetic field in the victim will not be cancelled. But usually, many people do this naturally. You can see this in my picture. I have a red and a black wire that are one close to the other. But what happened with the common mode? The common mode is very, very dangerous because the loop is uncontrolled. So you have the 12 volts line, you have the ground line, and then you have common mode going in this direction. In typical application, if common mode current is more than 10 to 15 microamps, you will fail in radiated emissions at 3 meters. So you need to check that there is no activity in common mode in any of the cables coming out from your product. Power supply, USB cables, audio cables, HDMI cables, I don't know, any cable with more than 10 to 15 microamps of current in a frequency range from 30 megahertz up to 400 megahertz, for example, is a candidate to fail in radiated emissions. So let's try to scan this cable with a scanner. We go again to the scanner. Let's try to do a new spectral spatial scan. Let me go to the settings. Let's go from 10 megahertz to 250 megahertz using 300 kilohertz in frequency. And let me activate other cells. In this case, I am interested in cells from row 3 to row 8 and up to column U. Row 3 to 8 and till U. I think this is let me select this one too, because the scan is fast. The scan process is fast, okay? So this is the area of interest. This is the area where I have my cable in position. So let's go here and let's run the test. Now, again, I will be testing the full number of cells I have selected in the full frequency range from 10 megahertz up to 250 kilohertz. Okay, you can see that the system is finding energy at 130 megahertz. So really, we have activity at this frequency in the cable. There is no filters. We will see where is the origin of this signal later. You can see that in the area of row number 5 is blue color. Let me reduce the reset zoom, okay? And make a new zoom here, okay? This is the activity I am identifying, okay? Let me find this is the frequency 130 megahertz. So let's run a test, spatial test. Let me create a node spatial at 130 megahertz with a 300 kilohertz resolution bandwidth. And let me specify the same number of cells. Is from the 3 this to you, this one, okay, accept, and then we scan only for that frequency. That is the problem. This is the frequency where I am failing in radiated emissions. Okay, the system is on, correct? Okay, you can see here the activity. So one possibility to avoid the emissions from this product is to introduce impedance, no? So if we go to the slides again, we know that if you have a product, this is a metallic enclosure, and we have the red line and the black line with ground, and we have common mode current going in this direction, okay? This is something like you have a monopole, okay? It's something like you have some kind of radiation surface. We have the arm of a monopole, and then we are exciting this monopole between A and V with some kind of voltage. This is the voltage that is exciting the monopole, no? Obviously, this is not a perfect monopole because the position of the cable is not perfectly perpendicular to an infinite radiation pattern, but this is the idea to evaluate. So how much is the current at the end? How much is the current if this cable is open? The current here is 0, but it's not 0 in the middle, okay? So you are radiating because you are injecting current. The electric field that you have at some distance is proportional to this current. So if you reduce this current 10 dBs, the electric field will be reduced 10 dBs at 3 meters. How you can reduce the injection of this current? The first possibility is to go inside of your PCBs and to destroy the voltage, to make the voltage equal to 0. So there will not be excitation. In our demo, instead of doing this voltage equal to 0, we need to go inside of the product. What I am going to put here is a ferrite. We select a ferrite with an impedance that match the frequency we want to kill. If you have impedance, the current will be reduced. So if our frequency is 125, 130 megahertz, we need to locate a ferrite in the market with some kind of impedance at this frequency range. So let's go to the data sheets. Let's go to this ferrite from Burst Electronics. It's a ferrite to put in a cable in this way. We go into the information about impedance, and you can see that this ferrite, using only one turn at 120, 200 megahertz, is something like this, is around 200 ohms resistive impedance. That means we go here and to introduce here the Burst ferrite is something like introducing here 200 ohms of resistive impedance, and then the current will be reduced. Let's see if this happens, okay? So we go to the camera, and now we take the ferrite, we open the ferrite with this accessory, this way. Sorry. Oops, very okay. It's open, and let's introduce the ferrite in place. Okay. Sometimes this is not a good solution because it's ugly or it's expensive or it's impossible. There is no space for this ferrite, but it's a typical solution. It's a last minute solution for many, many products. So now I can repeat the test. And let me see if this is working. Sometimes EMI fail in the demos. That is because demos are dangerous. No? So let's go to the scale option. Let's remove the auto scale option. Let's put here -3 to 33. Okay. This is from -3 to 33 is the situation without the ferrite. Let me put here open scan that data. This is without ferrite. Without. And this is with ferrite. This is with ferrite. With ferrite. Sometimes it's good to introduce comments, no? And now here, the auto scale option is removed. And here we have -3 to 33. So here is -3 to 33. Oops. Oh, it's not, it's reduces in some way. Let me go to, if we can change the scale. Okay, here. There's some reduction. It's not very, very big reduction, but you can see how the ferrite is affecting. Where must be the difference? Perhaps because I have some kind of loop in my analysis, no? You can see here that around FG columns, I have an increase in magnetic field, no? Let's go with a zoom here. Okay, let's go with a zoom here. Here, sorry, this way. And let's make a zoom. So you will understand where is the difference. You can see in my analysis, in my measurements in this area, I have red color in FG56. FG56. And what happened in FG56? The cables that were one very close to other suddenly are open. So here I have the loop, and the magnetic field created by this loop is bigger than the magnetic field that is created by these wires that are one close to the other. So to be able to measure the common mode current, I need to scan only the area where the cables are very close one to the other. So let's go here, settings, and the spatial probes will be activated only for column I, for example. So these columns will be deactivated. Why this area? Because in this area, the cables are very close one to the other. So I really will be able to see the common mode. Let me repeat the test. And then I will remove the ferrite. Later, we will see how is the differential mode current. Okay? This is the result in the area of interest. So now let's remove the ferrite. Sorry, it's not easy. Okay, we need to do this without big movements in the cable. Okay, now the ferrite is removed, and I repeat the test. So we will be able to compare really the effect of the ferrite in the common mode. Okay, now this is with, and this is without. This is without. But now only in the area of interest. In with, in auto scale, let's see, from -4 to 24. And now in without is the same, from -4 to 24. Okay, you can see the difference. This is without the ferrite, this is with the ferrite. Without the ferrite, with the ferrite. If you compare the measurements with and without the ferrite, you will have the insertion losses of this ferrite, 200 ohms, in this situation, in this position, at this frequency, and with the terminal impedances we have in this application. Remember this, if the cables are not very, very close one to the other, then you are measuring both common mode and differential mode. If you want to measure common mode, the two wires must be as close as possible. Let me see what happens if I open the loops. If I open the loops, like this, let me separate. Let me remove the tape this way. Let me remove the tape this way. And let me open to separate the paths. Okay, I will be using this tape for the red wire, the power supply wire, and this is for the ground. Okay, this is very important because the magnetic field created by differential mode currents can be very dangerous for circuits that are on top of this area. Okay, you can see now that the area of interest for me is this area here, no? So I go to the spatial settings, and then for this same frequency, 130 megahertz, 300 kilohertz in bandwidth, instead of these rows, I am going to these cells. Let's go to move this screen. Let's activate here these probes here. For example, this area here. Let's be generous to the U here. Select. Okay, this area here. So let's run the test. Now you will see how effective is the differential mode current that is big in amplitude, bigger than common mode current, to create a strong magnetic field. Okay, you can see here. Oh, sorry. You can see here how is the loop created by the magnetic field. Usually, when you see that the current is taking some blue color between different points in the cable, this is because the cable has some kind of nulls in current. No? One possibility is that the distance between these points in length is lambda over 4 at the frequency of interest. No? Okay, so we are controlling the shielding effects. We are controlling the cables. Now we can open the circuit, and we can identify the emissions from the PCB. No? Cornell, I don't know if we are very bad on time, so feel free to say me that we are out of time.
Okay. I think we're still okay. We're within the time frame, so
okay.
You could continue.
Perfect. I will do the scan. Let me go out of the product with the PCBs. Now we extracting this carefully. Okay. So now I am interested in testing my product. And for testing my product, I will be using my power supply and my digital circuit. Okay. Now you are interested in debugging the circuit at the PCB level. You can combine two PCBs or you can use only one PCB at a time. So let's connect the power supply cable. In this way, let's connect the output from the DC-DC converter and let's power the DC-DC converter on my power supply. This is ground. And this is the power. Okay. So now the system is being tested. What we can do is to identify what is the origin of my 11 megahertz or my 126 megahertz. I can go here and I can run an spectral spatial scan. For example, from 10 to 250 megahertz using 300 kilohertz bandwidth. I am not going to measure peaks to identify exactly known, and I can select the cells that are of interest for me. Let me accept. Let me move this one. Let me open the settings again. Let me select the spectral cells. I go from column P to AF and to row number 16. So it's from P to AF. Perfect. This one. And then the DC-DC converter is here. It's in 11 till 20. And then the cable is in this area, more or less. Okay, so it's ready. Perhaps I can be interested in doing the overlay with a picture. So we can put a picture of my circuit adapted to the real dimensions of the circuit. I'm not going to do this very carefully. So it's not necessary. Okay, more or less this way. Accept, and then I can run the test. Okay. So now I am interested in finding where is the origin of the 11 megahertz and where is the origin of the 126, 130 megahertz signal. Okay, aquí reset zoom so we can scan the full number. Look at this in this area here. The main frequency is 11 megahertz. You can see in the spectral scan that the most important amplitude is coming from the first harmonic of the clock. And in the scanned area, this energy is in this area here. Okay, the other areas here are in blue color. The system is powered on. Okay, looks like 11 megahertz is coming through some trace in the PCB in this area. Let me reduce the size of this window so you can see here the picture. Okay. 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 Now you can see here that these colors switch to blue color because the dominant amplitude is here is at 132 megahertz. 132 megahertz. Wait a moment. Here again, we start to see some kind of green color. Obviously, the most important area is related with this mountain in 126 megahertz and is on top of the DC-DC converter. The DC-DC converter I am using here. Okay, so you can see how is the DC-DC converter. This is my DC-DC converter, where I am going into the circuit with around 9 volts, 10 volts, 10 volts here. And you can see this is the TPS 5410D. We have one inductor and we have the diode here to go out with 5 volts. Okay, this is the area of interest. You can see that the 123 megahertz is here, and the first harmonic, the 11 megahertz harmonic, is in this area here. Okay, let's increase. Okay, let me do zoom and let me add the overlay. No, so if I am interested in locating, let me make more transparent the picture. Okay, so if you are interested in where is the 11 megahertz, you make here click and you discover that the 11 megahertz is here. You are interested in the third harmonic, for example. This is the third harmonic. No, this is the not the third harmonic. This is the third harmonic here. You can see that this in this area. But if you are interested in the 126 megahertz, you can identify that this in this area, and we can see the picture in 3D, so to identify where is exactly. Really, the most important area related with the 130 megahertz is going to the schematic, this area here. Okay, this is the most dangerous area where we are creating 130 megahertz. Is the area on top of the inductor and the area related with the output of the DC-DC converter and the switching diode. No, this is related typically because I have some kind of ringing because of the parasitic inductances in the layout of my circuit. If we switch to the spectrum, to the oscilloscope, and we make a reset, let me go to this view. Okay, if we go to the oscilloscope, I can use a passive probe to connect to channel number 1, press it, and then when you are interested in looking at the switching activity of any power electronic circuit, remember that you need to remove, let me open here this picture. Okay, this one. Okay, this way. We need to remove the cap of the probe, and then we need to prepare some kind of accessory to avoid pigtails while measuring. What I usually do is to take a piece of wire, okay, to take a piece of wire like this one, remove the plastic, you cut, connect here, and then you can do something like this, is to make several turns around the ground shield of the probe, 2 or 3 turns, and then you cut here. Okay, so you have here this let me see if I can focus. Okay, you can see that there is no pigtail. Is forbidden to use this long pigtail. This is 200 nanohenries or something like that. And I usually work with this kind of sockets. No, so I have 2 sockets here, so I can connect my probe for measuring how is the activity, the switching activity of this device. Okay, without the pigtail. The pigtail can create ringing that is not in your circuit, is created by your measurement. So you can see how is the switching activity of the transistor. We can see the general view. Okay, and we can see that for the typical switching frequency of this DC-DC converter. This DC-DC converter is switching at 500 kilohertz. You can see how duty cycle is moved, but you can see how is this ringing in this area here. No? So we can open here. We see the ringing. That is exactly on top of the area we have detected with the scanner. We go to the marker, and then with the markers, I can go from peak to peak, and then we have here a difference from 8 nanoseconds, that is around 123 megahertz. This is the origin of the 126 megahertz we are finding in our product. Okay, you can see here. This is the origin. So you can go to the circuit, you can review the layout, you can introduce some kind of a snubber, or you can introduce some kind of ferrite to kill this ringing, so the emissions are solved. Perhaps you will have leakage in your enclosure, perhaps you will not have ferrites in your cables, but because you are killing this noise, the system will be very quiet. This must be done at the PCB level.